Okay, in this first lecture, I'm going to discuss why people are interested in studying differential equations, basically to motivate what we're going to do for the rest of the semester. And for that, I'm going to consider several problems, maybe from physics and possibly biology, that you should be already familiar with from our classes or just from the everyday experience. So problem number one, let's talk about the falling body. So let's suppose that we have the following setup, a ground and a ball of a mass maybe m. That is falling down to the ground that initially is at the height h, and then it falls to the ground at a certain time. And what we want to do is to describe the position of the mass at any moment of time and also possibly answer questions when the mass is going to hit the ground or whatever else we want to find out. So basically, we want to determine the position of the body at any given moment of time. Now, in this case, the position of the body is given to you by its height because it falls straight down. So we're going to introduce a vertical axis x, and x equal to 0 is going to correspond to the position of the ground. So then the position of the body at the time t, so position of the body at time t, or of the ball in this case, is given to us by the function x of t. And you can use whatever units you would like to use, meters, centimeters, kilometers, whatever. So then, at the time 0, I'm going to assume that I know that the height is, or the position, in fact, because the time is 0, so let's just call this x of 0, that this is equal to some x0, so that's initial height. Okay, and so what we want to do is we want to find x of t. Okay, so how can we do that? Now we have to appeal to physics. So if I want to solve the mechanical problem when the body is moving subject to some external forces, then you might recall that the forces always satisfy the second Newton's law. So we're going to use the second Newton's law, which says that mass times acceleration is equal to the force. Okay, so what do we know in this case? We know that the only force that acts on the body, in fact, we're going to make an assumption, assume that there is no air resistance in this case. And so then the only force that acts upon the body is a gravity force, mass times gravitational acceleration. And so then, what do we know? We know that mass times acceleration must be the same thing as a gravity force. So in this case, notice that the gravity force is acting in a direction opposite to the direction of x-axis. So the gravity force must be equal to minus mg. And so we can cancel m because clearly the mass of the body is not zero. If it was zero, then gravity is irrelevant. And so what we get is that a is equal to minus g. And let's say I want to use a SI system. So then here g is a standard gravitational acceleration, and that is 9.81 meters per second squared. All right, so I know then the acceleration of my body at any, not my body, but of this ball at any moment of time. And so if I know acceleration, would I be able to find position? So in this case, we need to recall a couple of things. So I'm going to recall that number one, what is the relationship between the position and velocity? So if position is x of t, and velocity, let's say, is equal to v of t, then what is a velocity? Velocity is a rate of change, instantaneous rate of change of position. And so what we have is that x prime of t is v of t. Okay, and number two, if velocity is v of t, and acceleration is a of t, as we already labeled it, then again, what is acceleration? Acceleration is a rate of change, instantaneous rate of change of velocity. So then what we have is that v prime of t is the same thing as a of t. And so now if we combine 1 and 2, then we get the following. We get that if I take x double prime of t, then x double prime is x prime of t prime, which is according to 1 v of t prime, that is v prime of t, and from 2 this is a of t. And so what we get, because in this case gravitational acceleration is minus g, what we have is that in our case x double prime of t must be equal to minus g. And we know that g is a constant minus 9.81. So g, just to re-emphasize this, g is a constant. All right, so then what we got is an equation. So this is an equation for an unknown function of x, and the goal is to find the solution of this equation, right? For the goal is to find x of t. All right, so how can we solve this equation? Well, if I know the derivative of something, then I clearly can figure out what x of t is by integrating, right? So first, so to solve, we need to integrate. So if x double prime of t is minus g, then I can figure out what x prime is, again, by integrating both sides. So x prime of t is an integral of x double prime of t dt, right? X prime is an antiderivative of x double prime. So in this case, what I'm doing, I'm integrating x double prime, which is equal to minus g. So this is minus integral of g dt. And g is a constant, so integral of a constant is that constant times t. So minus gt plus some constant, which I'm going to call c1. Okay, but the goal is not to find x prime of t. And by the way, in this case, if we recall what x prime means, x prime is precisely the velocity. So I can actually write this as v of t equal to x prime of t. So v of t is c1 minus gt. So velocity in this case is going to be a linear function of time. Okay, so now if I know v of t, or if I know x prime, then I can figure out what x is. So x of t is an integral of x prime of t dt. And it is the same thing then as an integral of v of t dt, either one, right? And that's an integral of that expression that we found on the previous line. So it's an integral of c1 minus gt dt. Once again, c1 and g are both constants. So this is an integral of c1 dt minus, I can pull g out of a second integral, minus g integral of t dt. So what we get is c1 t minus g, and integral of t is t squared over 2. And because we're taking an indefinite integral, then we need to add another constant, and that's the reason why I had c1 here, because that other constant is different from the first one, so it must be c2. Okay, so then what did we do? We solved the equation x double prime of t equal to minus g by integrating twice. And we found the solution, this function x of t, which is supposed to give us a position of the mass above ground at any moment of time. Indeed, we have some function of time here on the right. But there is a problem, because in this function you have two generic constants, c1 and c2. And clearly then you did not actually solve anything, because you still cannot predict anything because you don't know the constants. So we have to find some way of figuring out what the constants are. And there are some things that we have not used yet, right? Because one more thing that we know is not only that x prime of t is equal to minus g, or that a is equal to minus g, but we also know that at the time 0, the ball is above the ground by x0 meters, right? Not only that, but we also, clearly, actually, the answer is going to depend on whether or not you just release the ball x0 meters above the ground, or maybe at the time 0 you threw it upward or you threw it downward. So in addition to the initial position, initial velocity also matters. So What we're going to do here, to determine C1 and C2, what we need, we're going to use the condition that x0, x at time 0, is equal to x0. And also, I'm going to assume that the ball was released from rest. And that means that the initial velocity of the ball would be equal to 0. And that statement, of course, is equivalent to x prime of 0 being equal to 0. All right, so then what do we have? We have that what is x of 0 from my equation. So let me label it by, so from the solution, we know that x of 0, which I want to be equal to x0, right? That's my condition that was imposed, that I imposed in the beginning. But what is x of 0? It's the same thing as what I got here with t replaced by 0. So if I replace t by 0, I'm going to have c1 times 0 minus g over 2 times 0 squared plus c2. This is 0. This is 0. So the whole thing is equal to c2. And so from this condition, we deduce that c2 must be the same thing as x0. Now also, v of 0 on one hand is equal to 0 again, because again the ball was released from rest. But on the other hand, v of t is given by this equation. So v of 0 is going to be this expression with t substituted by 0. So v of 0 is equal to minus g times 0 plus c1. And that means that c1 is equal to 0. And so now to summarize, what we did, we solved the following combination of equations. Number one, we had x double prime of t equal to minus g. We were given that x at the time 0 is equal to x0, and we're given also that x prime at time 0 is equal to 0. That's a condition of rest. So we solve the problem like this, and the solution ended up being what? So it is the expression for x of t here. And we determined that c2 is equal to x0 and c1 is equal to 0. So that means what we got is x of t is equal to x0 minus gt squared over 2. So x0 is given to you, g you know, so that means that x of t is known at all times. So in particular, if I want to find the point or the time when the ball will hit the ground, I just need to solve an equation for t when x of t is equal to 0, but I'm not going to do that here. A note about the terminology. So the equation here is an equation that involves derivatives of an unknown function, like we said before. And the goal is to find the function itself. So any equation that involves derivatives of an unknown function is going to be called a differential equation. So this would be a particular example of a differential equation. So in fact, we solved it, right? So you already then know enough to solve at least simple differential equations. So the question might be, why do we need the entire course to study this sort of problems? And you'll see later on, in fact, later on today, that not all equations, all differential equations are going to be as easy to solve as this one. So another point is that the solution of a differential equation, in this case, it was a differential equation that involves a second derivative. So solving this equation involved integrating this equation twice, and integrating the equation twice produced two unknown constants C1 and C2. So the solution of a differential equation actually is not unique, that you can have infinitely many different solutions in this case, and you can extract one solution out of those by specifying these two unknown constants. And to specify two unknown constants, and we had to prescribe two conditions, which specified what the ball was doing at the time t equal to 0. So for that reason, these are called initial conditions. And the whole thing is called an initial value problem. So the whole combination of a differential equation and initial conditions is called an initial value problem. And that is something that we will be interested to solve in the future. So let me write this down here. This is an initial value problem that we will abbreviate in the future as an IVP. All right, so that's example number 1. Let's look at the example number 2. Let's see if I did label this. Okay. So example number 2. Let's look at the problem where you consider radioactive decay. So let's say you have some radioactive substance. So maybe initially have some radioactive substance in a sample of mass m0. And I want to find, and let's say even this, so of mass m0 with half-life call it T1 half, right? So M0 and T1 half are two known constants. And the question is, what is the mass of the sample at time t? So we know for sure now, first of all, what does T1 half mean? So what we know for sure is that if initially, actually, let's do some, introduce some notation. So suppose the mass of the sample at time t is some unknown function m of t. So some facts that we know. Number one, because we're dealing with radioactive decay, the mass of a sample is going to decrease with time. So m of t is a decreasing function. And because it is a decreasing function, as long as it is differentiable, so therefore m prime of t is always less than zero, right? Because the sample decays at all times. All right, number two, we know that mass at t plus t1 half. So whenever I consider some mass at the time t, if I add the half-life time to t, then what should I expect? I should expect to have 1/2 of a sample, mass of a sample left. So this would be 1/2 m of t. So every time I wait capital T 1/2, let's say if we measure this in hours or days, then at the end I will always have 1/2 of what I had at the time when I started counting. So in particular, m of t 1/2, if I start counting at 0, is 1/2 of how much I had at the time 0. And my assumption was that initially we had the mass m0, right? Sample of a mass m0. So this one is the same thing as, oops, sorry. This is the same thing as 1/2 m0. All right, what else can we say here? So derivative is negative. So maybe item number 3. So if you have a radioactive sample, then you would expect that this sample decays at all of its points, right? It doesn't decay just at the center or on the surface. Every single piece, chunk that you extract, you can extract from the sample will decay at the same rate. So that means that the more mass you have, the faster that mass will decay, because the more mass you have, the more mass you will lose at any moment of time. So larger samples decay more quickly. If that is the case, then I can make the following assumption. So we will make the following simple assumption, which will not contradict physics here. So physics, again, says that the mass must decay quicker if it is larger. How do you measure the decay of the mass? So rate of decay, instantaneous rate of decay, which is given by the rate at which mass, instantaneous rate at which mass is changing with time. So rate of decay is equal to m prime of t. So I'm going to assume that it is proportional to the mass at time t. So therefore, m prime of t is equal to I'm going to write minus k times m of t. So this then corresponds to the intuition, so that the rate of change of mass is proportional to the mass. The larger the sample, the faster it decays. So minus k is a coefficient of proportionality. And why am I using the minus sign? Because I said that the sample must always decay. So m prime always must be positive. So where minus in front of k and by the way, so in this case, then we have to assume that k is positive. So this thing guarantees decay. Okay, so what have we got then? So then we got that m prime must be m prime of t must be equal to minus k m of t. And what is that? That's again an equation for an unknown mass, unknown function of t, that involves derivatives. So this must be a differential equation. And in addition to the differential equation, what do we know? We know that mass at the time 0 we assume to be m0. So what is this? That's an initial condition. And so then together they will form an initial value problem. Now in previous case, I needed two initial conditions. In this case, would one initial condition be enough? And I claim yes, because in the previous example, the derivative was a second derivative. So at the end of the day, after integrating, we had two unknown constants. But in this case, it is the equation only involves the first derivative of m. So integration will produce a single constant. So that means that it would be sufficient to impose one initial condition to determine that constant. Okay, so we got our initial value problem. So that's our IVP again. How would I solve this initial value problem? Let's try. So what we have is that m prime is equal to minus km. K again is a positive constant. So I'm trying to solve. So then if I just follow the same procedure as before, so if I know derivative, how would I find my function? I would need to integrate. So integrate both sides of this equation. Integral of m prime of t dt. This must be equal to m of t, right? Because antiderivative of m prime is m. And then the right-hand side of the equation is minus km, so this must be equal to minus k. I can pull out a constant. Integral of m of t dt. So at the end of the day, integrating produces the following expression. M of t is equal to minus k integral of m of t dt. And then immediately, a huge difference with the previous problem is that now I need to integrate m of t to find m of t. So m of t is still unknown. And because it is an unknown, so the integral cannot be evaluated. Explicit. Okay, so then we hit an obstacle, right? Clearly, we know that the physical problem has a solution. So there are decaying radioactive samples. It's kind of obvious that this initial value problem describes that physical process, so we expect that it would have a solution. But this method of solving, which just involves blindly integrating both sides of your differential equation, certainly it's not going to work it because we don't know what the function is. So then at this stage, I'm basically reduced to trying to guess. So I'm going to try guessing the solution. In the future, of course, instead of guessing, we will develop methods that will allow us to solve these equations immediately without making any guesses. We will know exactly what to do when we see an equation like this, but at this point, because I don't know the method of solving, I will simply guess. So what do we guess in this case? We expect that the derivative of m must look like m itself with a factor of minus k in front. So which function produces itself after you take a derivative? And clearly, a function like that would be an exponential. So I'm going to try m of t equal to, now, if I just take e to the power t, derivative of e to the power t is itself. That's not what I have here. I have minus k times itself. But then what should work is e to the minus kt. So let's check. We're going to check. So what is m prime of t? That's e to the minus k t times minus k, right? So by using the chain rule, which is the same thing as minus k, but what is e to the minus kt? E to the minus kt is m of t. So this is minus k times m of t. So success, right? This m prime is equal to minus km means that our function indeed satisfies this equation. All right, but I still need to satisfy the initial condition, right? So in this case, I don't actually have any unknown constants, right? M of t equal to e to the minus kt. I know precisely what it is because supposedly coefficient minus k is given to me, or some coefficient k is given to me because uh, it must be somewhere in the conditions of the problem. So where does the unknown constant go, right? Because somewhere there must have been integration that I was doing. All right. So how do we incorporate the unknown constant? So one thing, since we're guessing still, so is it true? So can it be true? That just like in the previous case, m of t is e to the minus kt plus c, right? Because again, integration was involved somewhere. I'm integrating, and then I need to add an unknown constant. Well, let's see. What is m prime of t in this case? So m prime of t is still, right, derivative of the constant is 0. It's still minus k e to the minus kt. Well, and what is that? That is minus k times e to the minus kt, but e to the minus kt is not exactly m. We need to solve this circle equation with respect to e to the minus kt, and what we will get is minus k times m of t minus c. That's a problem. This is a wrong equation, right? That's not the equation that m is supposed to be satisfying. So adding a constant is not correct in this case. You cannot add a constant. All right, so I'm at a total loss here. So what else can I do? I can add something. Well, maybe I can multiply it by something. So I'm going to try m of t equal to c e to the minus kt. Okay, so what happens in this case? M prime of t is going to be c times e to the minus kt times minus k, right? Because again, I'm using the chain rule. What is that? That is the same thing as minus k times c e to the minus kt. And who is c to the minus kt? That's exactly m of t. So minus k times m of t. And that exactly is a correct equation. So this m satisfies the correct equation. Let me label it as star here. Okay, so now then no matter what c is, m of t like that is a solution. And so now I can try to, so again, this is a solution that involves an unknown constant. So now I can try to solve my initial value problem. By using the initial condition. So what does the initial condition say? I know that m of 0 must be equal to m0, which is the same thing as this expression at t equal to 0. So this is c e to the minus k times 0. So this is c. And so therefore, c is m0. So m of t must be m0 e to the minus k. So that is going to be an expression for the mass at the time t in your radioactive decay. So the mass is going to decay exponentially. One thing which I'm not going to do here, but we're going to do it in the future. In the beginning, I did not tell you anything about this constant k. What I said is that uh, the mass, the radioactive substance, has a half-life equal to T1 half. So half-life equal to T1 half uh, describes how fast the decay is going to happen, right? The larger is half-life, the slower the sample is going to decay. And the smaller is half-life, the faster the sample will decay. So T1 half, right, is going to describe the rate of radioactive decay. And in my equation here, what else describes the rate of radioactive decay is it is this constant K. So therefore, K must be related to T1 half, but at this point, we're not going to explore this relationship. Later on, we're going to look at this problem in depth, and actually the relationship is, in fact, very simple. So I'm just going to write here that the note that K must be related to half-life T1 half. All right, and very quickly, one more example where I'm going to be even more speculative. So let's suppose that we want to solve the following problem. So suppose that we have a bar one end of which is maintained at temperature T0, while the other end is at temperature T1. If uh, initially uh, let's say the temperature uh, across a bar is distributed in some prescribed way, what would the temperature be at every point in the bar at any time t. Okay, so again, let's say we have this bar. Let's say one end it is at the point 0, another end is at the point L. Temperature here is T0, here it is T1, so these are going to be fixed constants. Let's associate an x-axis with a bar. And so what I want to know temperature at every point x at any time t. Right, so temperature now is a function of two variables. And therefore, if I want to solve a problem similar to what I just did in the examples 1 and 2 that involve the differential equation, in this case, I can take derivatives with respect to two variables, x and t. So then, if this problem of a temperature distribution is governed by a differential equation, that differential equation must involve partial derivatives. Let's try to quickly reason out what sort of differential equation we may expect in this point for this problem. So what do we know already? What I've given you is that at the time 0, you have some temperature distribution. Let's call it T0 of x. I've given you that temperature at, did I say left, right? I said one and another. So let's say T of 0, 1 and point 0 is maintained at the temperature T. Okay, let me change notation here. Say call this T initial, T0, that's a constant. T at another end, T of L, is another constant. Right, so we know what the distribution of temperature in the bar is initially. We know that one end, the left end, is maintained at temperature T0, right end is maintained at the temperature T1. Okay, so one thing which probably is going to make sense relatively easily, if the temperature distribution in the bar is linear, then the experience says that probably then, so if the temperature is gradually rising between the point 0 and the point 1 in a linear way, then you probably would expect that the temperature is not going to change. When the temperature is going to change is when at some point it rises and then drops. So for instance, let me just give you two possible temperature distributions. So one, so this is 0, this is L, this is X, and this is temperature T. Let's say in one case, this is T0, and this would be T1. Let's say the temperature gradually rising from 0 to 1. So then it doesn't take too much time to realize that this temperature profile will not change. In time, for the simple reason that heat is just going to flow from the hotter endpoint here to the colder endpoint, but otherwise temperature is not going to change at any point in the bar. On the other hand, if we have a picture like this, so XL T0 and then T1, and we had maybe a temperature profile that looks like so, then in this case, you would expect that the temperature profile is going to change because obviously the temperature is low here, but it's higher everywhere nearby. So what will happen is that heat will flow from this region and this region towards here. And so the temperature as a result will rise at a point that is circled now, and it will probably fall at the points here and here. So therefore, so this temperature profile is not stationary. And it will change. Okay, and so then what is the conclusion that we can draw from this? The conclusion is that what drives the temperature change is going to be not the temperature itself, right? Because if temperature is constant everywhere, then there is no change in temperature. If a temperature is linear like this, there is not going to be any change of temperature and time because temperature profile is happy. So the drive in temperature change is going to be driven not by a function or its derivative, but its second derivative, right? It's a fact that we have regions where you have minima, and local maximum in temperature profile. These are the things that will drive the temperature change. So very roughly speaking, then, I can make the following claim. I'm not going to justify it in any way. So we can assume then, so we can assume or conclude that the rate of change of temperature with respect to time, let's say at the easiest possible level, that this is proportional maybe to the second derivative of the time function t with respect to x variable, right? Because so here we're talking about the concavity of the function t of x, and whenever this function has second derivative that is not equal to 0, you would expect to see temperature change in time. So you would expect that derivative of t with respect to time is also not 0. Okay, so then what did it end up with? In this case, then this is also a differential equation. That involves now partial derivatives. And the conditions that I listed here are going to be initial conditions, but so there's an initial condition right here, right? Condition at time 0. But now we're also prescribing temperature at the different points on the boundary of the bar. So we're going to call those initial and boundary conditions. And so what we got again is a differential equation like so. We got initial and boundary conditions here. So at the end of the day, we need to solve an initial boundary value problem that will allow us to determine the distribution of the temperature in the bar. And of course, solving this problem must be much more complicated than solving previous two problems, because now you have to solve an equation which involves two different kinds of derivatives. So to summarize in this class, actually, fortunately for you, we're not going to consider any differential equations that involve partial derivatives. So the example 3 is just for your general education. And we're only going to consider problems that are more complicated than what I showed you in 1 and 2, but the easy thing about them is that they're only going to involve ordinary derivatives. So just all functions will depend on one variable. And because those are ordinary derivatives, we're interested in solving ordinary differential equations rather than the partial differential equation that is circled here. So in the next lecture, then, we're going to discuss classifications of ordinary differential equations, which will be essential in devising the strategies for solving various differential equations.